to the square of the distance. Forgot the word. Square of the distance from the source.
The intensity of light is mean the MA, right?
The MA? Not MA exactly. Intensity of light is always power per area. Not even that, yes. It's going to have really weird units. Rinkin would probably come the closest at this point, your MR, Rinkin. So let's just take, not worry about the units of intensity too much. And let's say let's just say I1 equals to we'll just imagine we're talking about a light bulb. So a light bulb is easy to think about. The intensity is 15 watts per meter squared, power over area. But don't worry about the units too much for this example. What I want to know is what is the intensity I want you to tell me what the intensity is at 10 meters. If you know the intensity is 15 watts per meter squared at 3 meters, what is it at 10 meters? And I haven't built your formula for you yet, except symbolically like that. So you're going to have to take that and see if you can build this formula. Hopefully you're saying I1 over I2 is equal to 2 squared over D1 squared, where D is the distance. And this intensity is inversely proportional to distance equation. I1 D1 squared, I2 D2 squared. And now all you have to do is solve that equation for I2. However you like to do your algebra, your results should look like this. I2 is equal to 3 divided by 10 squared. Watts per meter squared. Does the answer seem to make physical sense? You got farther from the source. You started out 3 meters from the source. Now you're 10 meters from the source. The intensity got weaker. Went from 15 watts per meter squared down to 1.35 watts per meter squared. Doing okay? One more of the same thing. This one. The intensity at 3 meters is 15 watts per meter squared, same numbers we were using earlier. Where will the intensity be 60 watts per meter squared? And you're using the same equation. Put it together like that. Question is, can you solve for D2? We're doing okay here. surprised? No, not surprised. As long as it doesn't get worse than this, you're okay. Doesn't really get much worse than this. So if you're reasonably comfortable with this math, you know, this kind of algebra, you don't do a whole lot more, just a little bit more, not much. So breathe a sigh of relief. The math is not going to be terrible. Another sentence for you. Another proportionality. This one's slightly different. Back to photon absorption. Earlier we said photons are more likely to be absorbed in dense material. So the photon absorption also depends on photon energy. And the more energetic the photon is, the less likely it's going to be absorbed. So low energy photons, easy to absorb. High energy photons, not so easy to absorb. And this proportionality is expressed as inversely proportional to the energy cubed. See if you can put together an expression that would express this proportionality as a formula. And in case you're wondering where this occurs in the book, the actual usage of this occurs in chapter 9. I'm not trying to get you there, I just want you to be able to use the proportionalities. Proportionalities comes up in many of the chapters, but this particular one comes up in chapter 9.
So energy is represented by E here?
Sure,
or?
that would be great. E is a very good one for energy. Yeah.
So what is the energy cubic?
Cubed. The third power. Third power of the energy.
How do you just P equals 1 over 8.
It's inversely proportional, so we're going to put the 2 there, and we're going to raise it to the third power. E1 here, also to the third power. P represents the probability of absorption. E represents the energy. Did you come up with anything that looks remotely similar to this? No? Yeah, that's good. All right. A question? Questions like you'll see when we actually get to chapter 9, which tends to be about the last 3 weeks, last 2 weeks. And our photon energies are going to be measured in keVs, by the way. That's just a unit of energy. Don't worry about what it is. How much more likely is a 25 keV photon to be absorbed than a 75 keV? Low energy, more likely to be absorbed. Okay, the 25 keV is more likely. Now we want to find out how much more likely. And you might write down something that looks like that. This also gives you a chance to figure out on your calculators, how do you cube something? Probably have a exponent button somewhere on there, y to the x or something like that. Caret, some of them. I popped it into my calculator and I came up with 27. Did you pop it in and come up with the same number? All right, now for the all-important sentence that interprets that expression. It's the verbal component of the class.
The 25 kilo electron volt photon is 27 more likely to be absorbed than a 75 kilovolt photon.
Excellent. There you go. Do we all agree with that sentence? We'll write it down here for you.
Oh, so
That's 25%.
yeah, 25 y
So there's a
x.
sentence that explains what that
Well, that's
calculation
zero.
represents.
And
Yes.
Can you tell us how did you enter it into your calculator? What did you?
Oh, in my calculator, which happens to be a TI-83, I do 75, and then there's a caret key for power.
Uh-huh.
You might have a y to the x key or something like that.
Uh-huh.
I can't see it.
It's the caret key.
This one brings us to the power.
I don't have to press the second.
No,
So
it's
yeah,
the
75, I just use caret 3 divided by 25 caret 3.
Have you found it?
Uh-huh.
That's how I enter it into this calculator. Other calculators have a y to the x button, I believe, something like that. All right. So when you see the words inversely proportional, you're not going to worry about them too much. You're just going to know how to build your little equations and do whatever's asked, correct? You got several problems in the homework to deal with that. All right, it's time for exponential functions. So this is a typical exponential function. And the word exponential function, well, ignore function, we don't have to bother you with that one. What does this have any verbal meaning to you? Something is related to the blank.
Something to the power of something.
Something to the power of something, yes. It's something to do with the exponent, yes?
Yeah.
This tells you got something to do with the exponent. And what it means is that the variable occurs in the exponent. When you see this phrase.
Bless you.
Okay, so we have an exponent, and our variable is in the exponent. K is just some number. We're not going to worry about what that number is in particular. What is this creature doing here? It's not Pac-Man. What is it? What is E?
2.78 something something.
2.78 and change, yes. It's just a number. It's a rather important number if you're a mathematician. It's like one of the most important numbers on the planet next to pi. But if mathematicians in here, before I insult anybody, no, mathematicians. For us, it is really just 2.78 and change. It is just a number, but it's not a pretty number the way we think of pretty numbers. But it's just, find this E button on your calculator. And when you find it, what we want to calculate is e to the 1. E1, there we go.
Okay, 2.71.
2.718, dot, 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 dot. It goes on forever. Oh, you should have found that number. And the E is just a shorthand way of writing that number out so that we don't have to worry about it all the time. Okay, this function that this equation that we have here has two uses for us. It comes up in radioactive decay. And it also comes up in other things related to what you'll think of as an altogether different topic, but it has the same mathematical foundation. The half value layer. I mean, these are just topics where this equation comes up. Not that you have to worry about them today, but radioactive decay. And the other topic comes up in chapter, I'm thinking 7 or 8, I forget which, where the beam is absorbed by various aluminum plates that you're going to put in front of the beam. And you're going to measure how much energy the beam has by how many aluminum plates you need to stack in front of it to reduce its intensity. So that's where this comes from. But what we want to do here is just play around with some of the math involved in dealing with this equation. That's all we're going to do, play around with some math. And let's just try something, for example, N0, let's make that, 9,380. And let's make K equal to 0.2. And I need my equation back. N is equal to N0 e to the minus KT. What is N? And T is equal to